So till now we have studied about natural numbers that go 1, 2, 3 and so on. We have studied about whole numbers, which is 0, 1, 2, 3 and so on. Then by 7th standard we studied integers from negative infinity to -2, -1, 0, 1, 2 and so on up to infinity. And then we covered rational numbers last year, and we said that rational numbers are all those numbers which can be expressed in the form of p by q, where p and q are integers. This means belongs to integers. Okay, so p and q are integers and q not equal to 0. And then last year itself we also covered some peculiar type of numbers, just a bit of them, called the irrational numbers. Irrational numbers that are, let's say, root 2. These numbers, they never end and the pattern never repeats. So it's just a random bunch of numbers. Okay, so you cannot predict what's going to be the next or anything like that. So so till last year we covered all these real numbers and this is rational numbers. Okay, so we covered rational numbers, then irrational number last year, and this year we are going to cover something called real numbers. Real numbers are something that includes both the rational numbers and the irrational numbers. Okay, and let's get started. First, before starting this, I would like to talk about Euclid's division lemma that is actually deleted in our syllabus, but will be quite useful for the following operations or following questions that we do in this chapter. So I thought it might be important to cover. But first, before we cover, we need to understand a few concepts of LCM and HCF, mostly HCF for Euclid's division lemma. What is HCF? HCF basically means the highest common factor. So if you're given a few numbers and you're asked to find the HCF, so let's say you got 4 and 2. If you're asked to find the HCF, you need to find the biggest number that divides both 4 and 2. Okay, that is HCF. Now, what the Euclid's division lemma helps us to do is to find the HCF in a very quick way, unlike the ways that we have been taught at school currently. So, Euclid's division lemma states that if there are two numbers, let's say 424 and 24, and we are asked to find the HCF of both these numbers, what we have to do according to Euclid's division lemma is to take 424 equal to 24 multiplied by something plus a remainder. So we can see that 24 multiplied by 17 plus what? I think it's 16. Okay, so we can write it like this. Now, since this is not 0, we have to do this again but 24 comes to this side. That is, now it will become 24 equals 16 multiplied by something plus a remainder. So 16 multiplied by 1 plus 8. Now since the remainder is still not equal to 0, we have to continue. Same logic, 16 is equal to 8 times 2 plus 0. Now we stop here because this is 0. We do not have to continue any further. Since this is 0, we take what is just above. The remainder just above was 8, and the HCF of 424 and 24 is equal to 8 by the Euclid's division lemma. Now if you don't understand, you can just rewatch it, and if you still do not, don't worry, because this is deleted syllabus and questions will not come from exactly this. It just aids in problem solving, that's all. Now the next thing that we need to know is something called the fundamental theorem of arithmetic. The fundamental theorem of arithmetic states, if you have any number, it can be written as the product of prime numbers. This will be unique apart from the order. That is, let's say that you have a number 42. You can write 42 as the product of primes. What are primes? Primes are numbers with only two numbers that can divide them. So 1 and that number itself. So if you check 2 can only be divided by 1 and 2. 3 can only be divided by 1 and 3. 5 can only be divided by 1 and 5. 7, same logic, 11, 13, 17, 23. All these are primes. Now, since this is 10th standard, we only asked till 23. We only need till 23. So remember till then, okay? Remember some examples of prime till 23. Now 42 can be written as 2 multiplied by 3 multiplied by 7. How did I get it, you might ask? See, first write 42 and then draw this. Okay, now you check the first prime number 2. Does 2 go here? Yes. And you divide 42 by 2, you'll get 21. Now you see, if 2 goes here, no. Does 3 go here? Yes. So 21 divided by 3 will be 7. 2 multiplied by 3 multiplied by 7, that will be 42. So with the same logic, you can do that. Now, according to the fundamental theorem of arithmetic, this will be unique. So no other number will be equal to 2 into 3 into 7. No other numbers. Just 42 will be that. Now it also says apart from the order in which the primes occur. What that basically means is that 2 into 3 into 7 and 7 into 2 into 3 are basically the same thing. We all know that. Okay. It's just saying that this is unique. 2 into 3 into 7 only corresponds to 42. That is fundamental theorem of arithmetic. Now this is a major step for this chapter, as this chapter revolves around the fundamental theorem of arithmetic, well, most part, because the next part is actually about LCM and HCF. Let's take two numbers 42 and 24. 42 2 21 3 7, like we did before. So 42 is equal to 2 into 3 into 7. 24 will be equal to 2 goes 12, 12 again 2 goes 6, again 2 goes 3. So 12 will be equal to 2 into 2 into 2 into 3. Now before we continue, this is called the prime factorization of 42. These are called the prime factorization of 42. This is called the prime factorization of 12. Okay, and you can find the prime factorization by this method. Now if we continue, if you are asked to find the LCM of 42 and 12, try to see if there is anything common here. A 2 and a 2 are common. Okay, so you write 2. A 3 and a 3 is common, so you write 3. Now the rest of the numbers you need to write it. Rest of the numbers you need to write it for LCM, and the product of all these will be the LCM of 42 and 12. That is 6 times 2 times 2 times 7, that will be 168. This is the LCM of 42 and 12. What is LCM? LCM means a number. Okay, so here the number is 168. 168 is the least number that can be divided by 42 and 12. 168 is the least number that can be divided by 42 and 12. Now HCF of 42 and 12 is another case. HCF asks us to find which is common. Okay, so we have 2 and 2, that is common. 3 and 3, that is common again. So here 6 will be the HCF of 42 and 12. Now I have already explained what the meaning of HCF is, so I'm not going to do that again. And for this, Euclid's division lemma will help you a lot. Okay, that's it for LCM and HCF. The next is a simple property that you will like. LCM of two numbers, let the two numbers be A and B. LCM of A and B multiplied by the HCF of A and B will be equal to A multiplied by B. This is an interesting property, also a dangerous one, because the question paper will definitely have a question that asks you to prove this. So for this, find the LCM and the HCF of A and B, multiply them and multiply A and B, see if they are equal. So in the above case itself, let's see 42 and 12. We find the LCM of 42 and 12 as 168. We write 168. Multiplied by HCF of 42 and 12 will be 6. So we write 6. Now this will be equal to 42 and there is one mistake. So this is not 12, this is 24 actually. This is all 24. We did 24, I accidentally wrote 12. Okay, now it's LCM of 42 and 24, that will be 168. HCF of 42 and 24 will be equal to 6. Now we multiply 42 and 24. These two will be the same thing, that is what we say. So since I am lazy to multiply right now. 168 multiplied by 6, that would be 1008. Okay, and we are saying that this is equal to 42 multiplied by 24, which is again 1008. Now this will work for every number, and questions may come. They will give you two numbers and say that verify LCM into HCF is equal to A into B. So then you will find the LCM and then you will find the HCF. You will multiply them and see if A into B is the same as LCM into HCF. Okay, so that is a third part of the chapter over. Now the next is a sure 3-mark question that will come for the exam. We will do 3 variants of them that has a chance of coming. So you will be asked to prove that root 2 is irrational. So we know that root 2 is irrational, but then we can't say that we know, because we are asked to prove it. So how do we prove it? We use a method called contradiction. So first we assume that root 2 is rational. So we say assume root 2 is rational. Okay, but we know it's not, but keep it there. Assume root 2 is rational. Now if something is rational, we can write that as root 2 is equal to P by Q. Okay, P by Q, and here let's say that HCF of P and Q equal to 1. So you cannot take any more factors out of P and Q and cut them. This is the simplest fraction. HCF of P and Q is equal to 1. P and Q are integers and Q not equal to 0. Now if this is the case and I'm going to square both sides, okay, so if I square this side and I need to square this side, that is 2 is equal to P square by Q square. Okay, simple. Now you cross multiply and you will get 2Q square is equal to P square. Here is a 1. Okay, what does this mean? This means that 2 divides P square. If 2 divides P square, this means that 2 divides P. It's mandatory. Okay, so if 2 divides P square, then 2 must divide P. So if 2 divides P, then that means that P, I can write it as 2 multiplied by another integer K. I don't know what K is, but P is equal to 2K, right? Because 2 divides P. So in that case, we have already found out that 2Q square is equal to P square. We already found that. So 2Q square is equal to 2K whole square. Why? Because P is 2K. So P square is 2K the whole square. Now 2Q square is equal to 2 square is 4 and K square is K square. Cut 2 from both sides, or divide by 2. You divide by 2 on both sides, and it means Q square is equal to 2K square. Okay, now this means that 2 divides Q. This means 2 divides Q square, and again like before, that means 2 divides q. So what we have found out is that 2 divides p and q, but that's a mistake. That is a contradiction. That is contradiction. Why? That is because we have already found out that the HCF of P and Q are equal to 1. So if 2 divides both P and Q, that means that 1 is not the HCF, but it will be 2. So HCF of P and Q is wrong because here HCF of P and Q equal to 2. Okay, so we say that our original assumption. What was our original assumption? Our original assumption was that root 2 is rational. So our original assumption is wrong. So our original assumption is wrong. That implies that root 2 is irrational. Root 2 is irrational. So that's how we prove that root 2 is irrational. Actually, we should do a little more number of variants because there are a few types of such questions. Now we are asked to prove that 1 by root 2 is irrational. So just like above, we will assume that 1 by root 2 is we will assume that 1 by root 2 is rational. Okay, and 1 by root 2 can be written as P by Q. Okay, and just like before, where HCF of P and Q is 1, P and Q are integers and Q not equal to 0, just like before. Okay, now this implies that now I can switch this over. Okay, so 1 by root 2 I can write this as root 2 is equal to, I need to switch this over also, Q by P. Okay, so this means that Q by P means Q by P is rational. Q by P is rational. This will imply that root 2 is rational. So now we can actually do this, that root 2, but it is contradiction, as we know. Root 2 is irrational. So it is contradiction, as we know that root 2 is irrational. And since root 2 is irrational and these are implying that root 2 is rational, our original assumption is wrong. Okay, and that implies that 1 by root 2 is irrational. Now the next variant is something like 7 root 5. See, this is simple. Assume 7 root 5 is rational. So now since we need to say the same step again, I'm just going to copy this. We are saying that 7 root 5 can be expressed as p by q and all the same things that we did before. HCF of p and q is equal to 1 and p and q are integers and q not equal to 0. Okay, now root 5 will be equal to p by 7q, and if p by q is rational, p by 7q will be definitely rational. Okay, since p by q is rational, it implies that p by 7q is rational. That implies that root 5 is rational, but just like before, it is contradiction. Why? Because it is contradiction, as we know that root 5 is irrational. Our original assumption is wrong. That implies that 7 root 5 is actually irrational. There are 2 more variants of this. Uh, 6 plus root 2. So assume 6 plus root 2 is rational. So 6 plus root 2 can be expressed in the form of p by q, where just like before, HCF of p and q is equal to 1, p and q are integers and q not equal to 0. Okay, we have to write that in every single question. So now we can write that as root 2 is equal to p by q minus 6. That will be p minus 6q by q. See, if p by q is rational, p minus 6q by q is also rational. You need to write this down. Okay, in the actual answer you need to write, since p by q is rational, p minus 6q by q is also rational. That implies that root 2 is rational, but just like before, it is wrong, but it is a contradiction. As we know, root 2 is irrational. Our original assumption is wrong, and 6 plus root 2 is irrational. Now one more type. This type will be easy. 6 plus 2 root 2. So there is not much work here, almost the same as before. So let's say that 6, assume 6 plus 2 root 2 is rational, and if it is rational, we can write that as 6 plus 2 root 2 equal to p by q with all the above conditions. Okay, now I'm not copying. See, this now will become 2 root 2 equal to p minus 6q by q. Okay, and then root 2 can be easily written as p minus 6q by 2q. Okay, 2 will go to the other side and divide. So p minus 6q by 2q. Now if p by q is rational, this thing will also be rational. That will imply that root 2 is rational, but that is contradictory, because we know that root 2 is irrational. Our original assumption is wrong, and 6 plus 2 root 2 is irrational. So that's almost everything, right? or do we have something more? Yeah, there is just one more. So another type is root 3 minus or plus root 5, whatever it is, it doesn't matter. You just need to know how to calculate. So again we can write this as p by q with the above conditions. Now you need to square on both sides this time. So if you square, you will get root 3 the whole square, that is 3, plus minus root 5 the whole square, that is 5, minus 2 multiplied by root 15. Okay, by the a minus b whole square. A minus b whole square is equal to a square plus b square minus 2ab. A plus b whole square is equal to a square plus b square plus 2ab. So this will be equal to p square by q square. Okay, so now this will be equal to 8. Take 8 to the other side. So minus 2 root 15 is equal to p square minus 8 q square by q square. And then you just have to take the minus 2 to the other side and you will get root 15 is equal to p square minus 8q square minus 2q square. Now it is optional, but you can take the minus to like this, the minus like this. So this will be p square minus 8q square divided by 2q square. So you can take and put it here. Okay, and if p by q is rational, this will definitely be rational. Okay, that but we know that will imply that root 15 is rational, but we know that root 15 is not rational. So that implies our original assumption is wrong, and root 3 minus root 5 will be irrational. So these are the definite 3 markers that could come. So you need to pay extra attention on this. And the LCM into HCF is equal to A into B question, that will also definitely come. Now there is another simple type of problem that can come as a 2 marker, so I need to also discuss that. The question says, check whether 6 raised to n for any n, okay, for any n, I don't care what n it is, ends with 0. Okay, so will any value of 6 raised to n for any value of n in natural numbers, that is 6 raised to 1, 6 raised to 2 or anything like that, we need to check if it ends with 0. So what you need to do is to write, if a number raised to n, if a number raised to n ends in 0, okay, that implies that number should be divisible by both 2 and 5. So any number that can be divided by both 2 and 5, okay, they raised to n will end in 0. So let's see, 2 divides 6 obviously, but 5 does not divide 6. That implies 6 raised to n can never end in 0. Okay, so yeah, that's it for this entire chapter. So we discussed the main ideas of LCM and HCF, Euclid's division lemma, real numbers and things like that. We also discussed the fundamental theorem of arithmetic and problems, some important problems that could definitely come for the exam, some 3 markers and 2 markers. And this is it for the chapter.